Welcome to the video lecture on graphing tangents, cotangents, secants, and cosecants. We're going to start with the graph of tangent of x, and you want to recall that tangent, when we talked about properties of trig functions, we said that tangent had a period of pi, and we're going to see that on our graph in just a moment. To figure out how to graph it, we could plot some points, and I'm just going to use some of our common accepted values, pi over 3s, pi over 6, pi over 4 angles that we get from our unit circle. So if we pull up our unit circle here for a moment, remember that tangent is the y coordinate divided by the x coordinate of your terminal point. So if we take a look at a pi over 6 angle, that would be a 1/2 divided by a root 3 over 2. Those 2's are going to cancel, so that would simplify to a 1 over root 3. So any pi over 6 that I see in my chart is going to become a 1 over root 3. Then we have to think about quadrants. In quadrant 1, tangent is positive. In quadrant 2, tangent is negative. In quadrant 3, tangent is positive. And in quadrant 4, tangent is negative. Now if we look at pi over 6 angles, pi over 3 angles, then that's going to be a y value of root 3 over 2 divided by a 1/2. The 2's would cancel again, so this time we'll get a root 3 over a 1. So all of our pi over 3's just become square root of 3. And again, tangent is negative in quadrants 2 and 4. And then finally, the pi over 4's, your y value is root 2 over 2 and your x value is root 2 over 2. So when you divide those, they cancel out to a 1. So all of my pi over 4's are going to have 1, and in quadrant 2 and quadrant 4, tangent will be negative. Now when we think about the quadrant angles, for 0, for example, that is at the point 1, 0. So we're going to take 0 divided by 1, and that would stay 0. Whoops. So if I wanted to fill that in, this is going to be 0. But when I get to pi over 2, then I'm trying to take 1 and divide by 0, and I can't divide by 0, so pi over 2 becomes undefined for tangent. So this is 0, but this is undefined. At pi, the y value is 0, the x value is -1, so 0 divided by -1 will be 0. 3 pi over 2, the y value is -1, the x value is 0, so we're trying to divide by 0 again, so this becomes undefined, and 2 pi is just like 0, so that will also be 0. So here's our chart of values for tangent, and I'm just going to plot some of the common ones here, some of the major axis ones. At 0, we want to go through 0. At pi, we want to go through 0. And at 2 pi, we want to go through 0. At pi over 2, this became undefined. And you can kind of imagine what that's going to mean. We have all of these y values getting closer to 1, and all the x values are getting closer to 0. And when you have numbers that are getting closer to 0 in your denominator, that's going to make the fraction blow up and get big. 1 over something small gets big. So this is going to be going to an infinity, which means we're going to have vertical asymptotes at pi over 2 and 3 pi over 2. And that's because we have those undefined values for x. They don't make the tangent function exist. Since we're in quadrant 1 from 0 to pi over 2, all of those y's and x's will be positive. So if I take all of these x values that are positive in the bottom, 1 over something small that's positive is going to something big that's positive. So this infinity is going to be positive infinity. And what that means is this graph is going to blow up towards positive infinity when we're in quadrant 1. When we're in quadrant 2, all those tangent values are negative. So it's still going to go to infinity, but this time it's going to go to minus infinity because we're in quadrant 2 between here and here. Between pi and 3 pi over 2, we're in quadrant 3, and tangent is positive again. So this time it's going to blow up towards positive infinity, and then here to here is quadrant 4, and all those tangent values are negative again, so this is going to have to shoot down to minus infinity. You could plot additional points here, but you can kind of imagine what's going to have to happen. It's going to go through that 0 and continue going down. And you'll see those same asymptotes in the negative direction as well. So here is what the standard graph of tangent is going to look like. Okay, so it's kind of these just little squiggly lines, and you've got asymptotes at all these odd multiples at pi over 2. So let's fill in some of our key characteristics. What is the domain of the tangent function? Well, it's not defined everywhere because we do have these undefined places, these vertical asymptotes. So our domain is all reals except all of these places where we have vertical asymptotes, which are all of these odd multiples of pi over 2. So we're going to write that as 2k plus 1. That's a way to generate every odd number, every odd integer, and we're multiplying that by pi over 2. And we're assuming here that k is an integer. What would be the range of this tangent curve? Well, how low does it go and how high does it go? It shoots all the way down and all the way up. So our range is all real numbers, minus infinity to infinity. How about our symmetry? Well, you can tell right here on this graph in the middle, centered at the origin, that if you were to rotate this 180 degrees around the origin, you would get back the same graph. So that means it's got symmetry around the origin, which means that it's odd, which means that tangent of minus x is equal to minus tangent of x. If something is an odd function, you can take that negative, which is being multiplied by the x, and pull it out front and multiply the entire function by it. How about the period? If you look at this graph, putting in all my labels here, one full cycle of tangent is one of these squiggly lines, one of these squiggly shapes. I only need one of them, and they keep repeating themselves over and over again. How wide is it to cover one whole squiggle? Well, this goes from minus pi over 2 up to pi over 2, so that's a width of pi right there. So I need a width of pi to get one full cycle of tangent. So that means the period of tangent is just pi. Where do these graphs have intercepts? Where do they hit the x-axis? Well, this is hitting at 0, pi, 2 pi, minus 2 pi, all those multiples of pi. So we're going to write that as k pi, where k is an integer. And then finally, where do I have these vertical asymptotes? Well, that's going to be at all the places where this domain was undefined. So all of those odd multiples of pi over 2. So whenever x is equal to 2k plus 1 times pi over 2, where k is an integer. Now what's going to happen when we start taking some transformations of these tangent functions? Just like we did for the sines and the cosines, you could see a very general form of the tangent curve. There could be an a out front, a b, a c, and a d. If you have this coefficient b, you want to make sure that you factor it out first. The a is going to affect your vertical stretch or compression. There really isn't what you would normally think of it as an amplitude for sines and cosines. There really isn't one necessarily for tangents because the graph shoots all the way up and all the way down. However, the a does affect how steep and how flat it is. So the bigger that a gets, the steeper the graph is going to get, and the smaller that a gets, the flatter the graph will get. The b affects your horizontal stretch and compression, which always affects your period. So we are going to have a formula for calculating what the new period will be. Now for sines and cosines, the formula was always 2 pi divided by whatever b was. But this time, because we're talking about tangent and the normal period of tangent is just pi, our formula is going to be pi divided by whatever b is. So use this formula to figure out where what your new period is going to be. After you've factored out your b, what you're left with in these parentheses will be your phase shift. and that will tell you how much to move your graph left or right. And then finally, the constant d on the end will tell you how much to shift your graph up or down. So let's take a look at 2 tangent of x. This has this coefficient 2 up front, so this is going to cause us to have a vertical stretch by a factor of 2. Now normally for sines and cosines that would mean we'd have an amplitude of 2. In this case, it doesn't really look like an amplitude so much, but because it's bigger than 1, that is going to make our graph get steeper. So these tangent little waves or curves that you have here are just going to rise up towards infinity or shoot down towards minus infinity faster than they did before. Now we don't have any horizontal shifts or vertical shifts. We don't have a change in period at all. So we're really just taking this same tangent graph, which I've got a copy of down here, and the only thing we're changing about it is we're making it become steeper. So all these zeros aren't going to change because 0 times 2 will stay 0. But all these y values here are going to get multiplied by 2, which is going to make them get higher faster. So I would show that steepness by showing that red curve lying above this black one. And similarly over here, this is going to shoot down faster than it did before. So when you're trying to show it steeper, it almost becomes more linear instead of curvier, almost like a straight line. Everything else about the graph is staying exactly the same. We're not changing those asymptotes either because we didn't change our period. So we just made it look a little bit steeper. So what happens if I have a negative 1/2 out front? Well, the negative is a reflection and it's out front, so that's a reflection over the x-axis. So that's going to take all these tangent curves and flip them upside down. So now they're going to start high and end low like that. So they're going to decrease instead of increase. But we also have an amplitude change, or excuse me, a vertical compression change, because we have that 1/2 out front, which would normally look like a new amplitude if this was a sine or a cosine. So we have a vertical compression by a factor of 1/2. And what that is going to impact on my graph is instead of making the graph steeper, it's going to make it flatter. So it's not going to go quite as high as fast as it did before. So if this yellow graph here would be the normal tangent graph, I want my new flatter graph to lie below it and be a little bit flatter in the middle. So it would look something like that. So it's going to be a little bit closer to that x-axis than it normally would be. And it's kind of hard to show that, but you sometimes just exaggerate it a little bit just to emphasize the fact that it is a little bit flatter than before. Okay? Plus it's going in the opposite direction because of that negative. Alright, tangent of x minus pi over 4. What does that minus pi over 4 do? Well, it's a phase shift. We don't have a coefficient in front of x, so we don't have to worry about factoring anything out first. And because this is a minus, this means we want a phase shift to the right, pi over 4. So let's put in a couple of marks here. This is pi, so this asymptote right here is at pi over 2, which means this is pi over 4, this is 3 pi over 4. This would be negative pi over 4, negative pi over 2. So if we have a phase shift to the right, then that means this 0, 0, which would normally be right here, needs to get shifted to the right pi over 4. Likewise, all of these asymptotes get shifted. So normally this asymptote would be at minus pi over 2, and now I'm shifting it over to the right pi over 4. So now it's going to be here, and this one shifted to the right is now going to be here. So this dot that I have should now be centered between these two new asymptotes, and I'm not changing my amplitude or anything else, so it's just going to be your normal steepness and normal direction for that tangent curve, but it's just been shifted over. This one's going to get moved over, this 0 gets moved over, and your graph would look something like that. This gets shifted over, this 0 gets shifted over, and it looks like that. It's always a good idea to kind of place your asymptotes before you start sketching your graph so that you know where to fit your tangent curve in between. Okay? Let's try another one. 4 tangent 2x. So the 4 out front is going to be that vertical stretch by a factor of 4. And it's not really affecting amplitude so much as changing the steepness of our graph. So our graph should be steeper than it was before. But now we have this 2 being multiplied by x, and that is going to be a horizontal stretch or compression. Since this 2 is bigger than 1, it's actually going to be a compression by a factor of a half. And what that implies is we're going to have a new period. So the old period is pi, and what you're going to do to that pi is you're going to divide it by whatever this b is. So we're dividing it by that 2. So my new period is pi over 2. So here's how I would draw this. First of all, I don't have a phase shift. That's the first thing I would always consider when I'm graphing. Since I don't have one, then I'm still going to be centered at the origin like I normally would be. But instead of having this normal width of pi, because tangent has a period of pi, now I need to shrink that period in to pi over 2. So normally, since this has a width of pi, that means I would go pi over 2 to the left and pi over 2 to the right, so the whole width going across would be pi. Now we need to shrink that in so that my width going across is only pi over 2, but it still needs to be centered at the origin. So here's what we would have to do. If my full period is pi over 2, then I need to go half that distance to the right to get to my first asymptote, and half that distance to the left to get my second asymptote. So what's half of pi over 2? Pi over 4. So that means I'm going to have new asymptotes at pi over 4 and minus pi over 4. And my tangent graph is now going to be squeezed in between these two red lines. It's going to have the normal tangent shape, but because I have this vertical stretch by a factor of 4, it's going to be much steeper than it normally would be. So it's almost going to look like a straight line going diagonally up. Now once you know how to place that very first cycle, then you're going to be able to draw the rest of your asymptotes. So if I have this asymptote at pi over 4, then the next asymptote should be over pi over 2 from that, because this whole width here needs to be that period, that new period that we have. So I'd have another cycle of tangent looking like that. Here's my last asymptote. I'm going to go over pi over 2 from there, over another pi over 2 from there, and I'm going to draw in those steep tangent curves. And then I'm going to go pi over 2 to the left, another pi over 2 to the left, and another pi over 2 to the left. So try to find your very first cycle by figuring out what your period is, taking half of that and going half that distance to the right for your first asymptote, half that distance to the left for your second asymptote. And once you know where those two asymptotes should go, then you're just going to equally space them to get all the other ones. Okay, what would the graph of the absolute value of tangent of x become? Well, absolute value just takes anything that was positive and keeps it positive, and anything that's negative turns positive. So all of these points on my tangent curve are already positive, so the absolute value is not going to change them. But all these points down here are negative, so when I turn them positive, that just flips them over that x-axis, and you get this graph like that. And it's I'm not being able to graph it too well, but it should be kind of pointy right where it changes. So this is going to be pointy right at that intercept, because there's an abrupt change right there. So that's all it does. Absolute value just takes anything that was negative and reflects it over that x-axis. All right, let's graph cotangent. If we know the graph of tangent, then we know the graph of cotangent, because cotangent is just its reciprocal. So all we have to do is take 1 over all of these y values. So what I'm looking at here is the graph of tangent. So I want to do 1 over it to get the graph of cotangent. So let's start with the zeros, because zeros are always important. 0 on tangent becomes 1 over 0 on cotangent. And what does 1 over 0 do? It blows up to infinity and becomes an asymptote. So if I have a 0 at the origin, 1 over that is going to blow up and become undefined on the cotangent graph. So you are going to get a vertical asymptote at 0. Another 0 is at pi, so 1 over that becomes undefined. And then I have another 0 at 2 pi, so 1 over that becomes undefined. Over here at minus pi as well, and minus 2 pi. So now the asymptotes for cotangent occur at all these multiples of pi. Now let's see what happens in between. Now in the original tangent graph we had asymptotes already. So for example right here at pi over 2. That was a 1 over 0 when we were trying to calculate that on our unit circle. So when you take the reciprocal of that, that becomes a 0 over 1 using the ordered pair from the terminal point at 90 degrees. And 0 over 1 becomes a 0. So this asymptote becomes a 0. It's 1 over something infinite, and what's happening is that's turning into something small. So it's kind of this inverse relationship. 1 over something small gets big, 1 over something big gets small. So all of these asymptotes that we had on tangent now become zeros on cotangent. Okay? And then we need to figure out what's going to happen on either side of these asymptotes. So let's take a look at the behavior. As these points get closer and closer to 0, notice all of those y values are positive. So when I do 1 over those really tiny numbers, they're going to get really big, but since they're all positive, they're going to go to positive infinity. So since these are positive y's, the graph should shoot up to positive infinity. Now on this side over here, as we approach this asymptote, all of these are negative y values. So they're still getting close to 0 and still getting bigger when we do the reciprocal. But 1 over something small that's negative is going to shoot down to minus infinity. So all of these points, as they get closer to 0, are actually going to shoot down towards minus infinity on the reciprocal graph. So if we connect these pieces together, this is what it looks like. It has almost that same shape as a tangent, but notice this time it's starting high and ending low. So cotangent decreases, whereas tangent increased. And if I continue this pattern, you're just going to get those same shapes. So it's very similar in style to tangent, but a couple of key differences. Again, the fact that the graphs decrease instead of increasing, and also notice the difference in the asymptotes. Now the asymptotes are occurring at all those multiples of pi, whereas on tangent, all the asymptotes occurred at all those odd multiples of pi over 2. So this is your basic shape for cotangent. One of these little squiggles here represents one full cycle of cotangent, and it happens within this width of pi. So the period of cotangent is pi as well, just like the period of tangent was pi. Okay, so now what this graph represents here is that cotangent graph that we just developed, and you know that it is because it decreases and those asymptotes are at all those multiples of pi. So we want to now just take this graph and we want to find out what cotangent of x plus pi over 4 is, and this pi over 4 is just a phase shift, and since it's plus, it's actually going to go left pi over 4. So I'm just going to move all of my asymptotes to the left pi over 4. So if this asymptote here is at 0, left pi over 4 would put it right here. Left pi over 4, left pi over 4, left pi over 4. That's the only thing that's changing about this graph. So now I need to squeeze in that cotangent shape in between these two asymptotes. So it's going to have to look something like this. Okay, so same arcing shape, really nothing too major is happening, we're just moving everything over to the left. Okay, how about 2 cotangent 2x? So the 2 out front causes us to have a vertical stretch by a factor of 2, and that's going to make the graph get steeper. So these are going to shoot up higher and go down lower faster than before. The 2 that's next to that x, that's that horizontal compression by a factor of a half. So that causes us to have a new period. Same formula applies that we used for tangent. You take the normal period for tangent, which is pi, and we're dividing it by this b. So this time our new period is pi over 2. So how do we want to figure this out? Well, this time, since my normal asymptotes are between 0 and pi, we're going to shrink that distance down so that it's only got a width of pi over 2. So I'm still going to have this asymptote at 0. That's not changing since I don't have a phase shift at all. But instead of going all the way to pi to get my next asymptote, this time I'm only going to pi over 2 to get my next asymptote because I have that smaller period. So this time my asymptotes are going to occur every pi over 2 multiple. So pi over 2, then pi, then 3 pi over 2, then 2 pi, and so on. So you should have twice as many of them as you did before because we are compressing this period by half. So we should be able to fit twice as many cycles as before. Now here was that first one, 0 on the left, pi over 2 on the right, and in between those first 2 asymptotes I want to draw the cotangent shape, which is this decreasing shape, but I want to draw it a little bit steeper than normal because I have this coefficient of 2 out front. So just try to exaggerate that steepness just a tiny bit. And then just repeat that pattern in between every pair of asymptotes that we have. So you should have twice as many cotangent squiggles as we had before. And there's my graph. Okay, the next one here, secant of x minus pi over 4. Now there's a couple ways to do this. We have already talked about what the graph of secant looks like. I'm going to pull it up for you just so you can remind yourself what it looks like. And this was developed in the lecture talking about the graphs of sines and cosines. So there is a PDF file that you can refer to with all of these graphs on them. Here's the sine curve. Here's the typical cosine curve. Then we took the reciprocals of those to come up with the graph of cosecant and secant. And these were the graphs with those U shapes. They look the same. The only difference is that they're shifted over a little bit from each other. Okay? And then we've got the graph of tangent and cotangent that we just talked about. So you can take those graphs and you can certainly shift those if you memorize what those graphs look like. I'm going to show you a different way to figure this out based on reciprocal graphs and reviewing cosines and sines as well. So secant, first of all, is the reciprocal of cosine. So you could think of secant of x minus pi over 4 as 1 over cosine of x minus pi over 4. So what I'm going to show you, and the way I'm going to explain this, is to graph cosine of x minus 4 first, and then take its reciprocal. So this graph that you are seeing right here, this is the graph of cosine originally. And what we need to do to it next is find cosine of x minus 4, which is a phase shift to the right by pi over 4. So that's going to take this graph, here's pi over 2, and it's going to shift it to the right pi over 4. So instead of starting here, I'm going to move that to the right, and instead of stopping here, I'm going to move that to the right, and instead of having my min at pi, I'm going to move that to the right. So I would get this graph that does this. So there's now the new graph of cosine x minus pi over 4. All right, we're getting there. Now all I need to do is figure out what would be the reciprocal of that. And you can keep on going here to get the rest of this cycle if you want to get the full width going across. So how do I take the reciprocal of this graph? Well, what we would do first is think about those zeros. Any place where this red graph has a 0, when I do 1 over that 0, that becomes undefined. So those are going to become your your asymptotes on your secant graph. So any zeros become vertical asymptotes. So I have one here, and so on. Then we have those U-shapes. Wherever there's a maximum at a height of 1, 1 over 1 stays at 1. So this little peak is going to stay in that reciprocal. 1 over negative 1 stays negative 1. 1 over positive 1 stays positive 1. So those peaks and valleys don't change. But because we have these asymptotes, we're going to need to blow up towards infinity or minus infinity on either side. And there's an easy way to tell. It's just based on whether the original y values are positive or negative is going to tell you whether you blow up to positive infinity or negative infinity. So for example, all of these y values here in red, all of these y values here are positive. And as I get closer to 0, as I approach those asymptotes, 1 over something small that's positive is going to blow up to something big that's positive. So that means these have to blow up to positive infinities on either side, and I'm going to have to come down and hit that little peak. Over here, all of these are negative y values because they're below the x-axis. So these are going to shoot down to minus infinities. So this is going to have to do something like that. And then here we're back to positives. So these shoot up to positive infinity on either side, and it has to scoop down and hit that little blue dot. So you get these U-shapes again that have been shifted over slightly, and they still have their mins and maxes at 1s and minus 1s, but all these asymptotes have been shifted over slightly. So these red U's would be my final graph. Okay, let's try that again. This time we're going to look at secant of 2x. Again, that's the reciprocal of a cosine. So there's many ways to do this, but what I'm going to show you is how to think of it in terms of cosine of 2x. So secant of 2x is 1 over cosine of 2x. This is the graph of cosine, so let's find out what the graph of cosine 2x would become first. Now you have a 2 in there next to that x, so that means we're going to have a new period. We have a horizontal compression going on. Now remember, for cosine, the period is 2 pi. So we're going to divide that by this 2, so the new period needs to be pi. So we need to complete that normal U shape. Instead of from 0 to 2 pi, we need to complete it from 0 to pi. So we're going to need to do this U in a shorter width. So this would be my horizontal compression. I'm just completing twice as many U shapes as I normally would. That's all that that 2 does. It makes us do that full U shape from 0 to pi, start and finish it from 0 to pi, instead of having to go all the way to 2 pi to finish it. So now this red graph is cosine 2x. So to get secant of 2x, we want 1 over that. So all the zeros When I do 1 over those zeros, they become undefined. So anywhere where this red graph has a 0, that is now a new asymptote on my secant graph. So you have all these vertical asymptotes. Okay? Then all of these 1s and minus 1s, these maxes and mins, 1 over those stay 1 over 1 or 1 over negative 1. So they're going to stay at 1 and minus 1. Those won't change. Those blue dots will stay on both graphs. Then we just have to figure out whether our u should go up or should go down. All of these y values are positive, so as I get closer to 0, I'm going to have to blow up to positive infinity. So these are going to have to be a u that shoots up. All these y values here on this red graph are negative, so 1 over something negative is going to blow up to a negative infinity. So these have to shoot down. All of these are positive, so this u is going to be going up in the positive direction. All of these are negative, so this u is going to be shooting down. All of these are positive, so I go up, down, and so on. So you alternate back and forth. Okay? And there would be my new graph. Okay? Let's try negative 1/2 cosecant of 2x. Again, you can do this many different ways. If you have the graph of cosecant memorized, then this would really just be that cosecant graph with a revised sort of amplitude because of that negative 1/2 with the reflection, and also a new period because of this too. That's certainly a fine way to do the problem. I'm going to show you how to do this using the reciprocal function instead, just to kind of review how the sine curve works and also to review how to graph reciprocal graphs. So you have to be slightly careful on this because cosecant is 1 over sine. So this is really like sine of 2x, but where does that negative 1/2 fit in? The negative 1 would be on the top and the 2 would be on the bottom. And actually I'm going to take that negative, and just for the sake of making this a little easier, I'm going to stick it next to that 2. So what I'm going to graph first is I'm going to graph this whole denominator, negative 2 sine of 2x. This graph that you're looking at right here, this is that normal sine curve shape. So we need to revise this black graph and turn it into negative 2 sine 2x. And then we're going to take the reciprocal of that to get our cosecant graph. So first of all, let's figure out how to do these transformations. We have a negative, which is a reflection over the x-axis. We have this 2, which on a sine curve does affect your amplitude. So I'm going to have a new amplitude equal to 2. And I have this 2 next to the x, which is that horizontal compression. So we're going to have a new period. For sine, it's normally 2 pi, but now we're cutting it in half, so it just becomes pi. So we have to put all these pieces together. So normally, sine would start at 0 and complete one cycle and stop at 2 pi. But now we have a new period of pi, so I need to complete that whole sine curve from 0 to pi instead of 0 to 2 pi. So that means I'd have to go up and then down and finish at pi. So that's what the compression would do. But I have a new amplitude and I have a reflection as well. So we're going to have to stretch this guy up to 2 and minus 2, and then we have to flip that whole thing over. So what that's going to look like is instead of going up to 2 and down, we're actually going to need to go down to 2 because of the reflection, and then up to 2 and down like that. So there is my new sine curve. It's been flipped upside down, it's been stretched to have a new period of 2, and it's been compressed to have a new period of pi. So let's just copy this shape over and over again. And this, again, in red, is the graph of negative 2 sine 2x. Now to get my cosecant graph, I need to do 1 over this. So those zeros are the key things. Anytime you have a 0, 1 over that becomes undefined. So any zeros on this graph become the asymptotes. So we're going to have an asymptote here, here, at 0, at pi over 2, pi, and so on. Now, just to keep this in the back of your head so you sort of know what to expect, cosecant and secant are these U shapes that go up and go down. So that's kind of what I'm expecting to see. Now, be careful a little bit. Normally we say that these peaks and valleys stay where they're at because they're at a height of 1, but that doesn't quite happen here. Take a look at this little point right here. It's at a height of 2. What happens when I take the reciprocal of that? Well, 1 over 2 becomes a half. So instead of going this high, we actually, when we do its reciprocal, that shrinks it down and it goes down to a half. Let's try that again over here. This is at negative 2 originally, but I want the reciprocal of this. So what's the reciprocal of negative 2? Negative a half. So you're going to get all these little blue dots at positive 1/2 and negative 1/2. Those are going to be where your U's touch down at. Now, because this part of the graph is all negative, that means all my y values when I do the reciprocal should stay negative as well. So these are going to have to shoot down to my minus infinities. So this is going to have to be a downwards U. All of these are positive, so they're going to have to shoot up towards positive infinity. So I'm going to get an up U, then a down U, then an up U, then a down, then an up, and so on. So there's my cosecant graph. The little peaks and valleys go to 1/2 or minus 1/2 because of this amplitude change. And I have twice as many of them as I normally would because of the horizontal compression, and they're going in the opposite direction because of the reflection. So this is just one way to do it, using the sine curve, doing some transformations on it, and then taking the reciprocal. Okay, secant of x plus 1. Let's take a look at that graph. So this is going to be the graph of cosine that we're looking at right here. Okay, keep that in mind. There's that U shape. So if we want to use that to help us graph this, one way to do that would be to look at the graph of cosine and think of secant of x as 1 over cosine x. Now you have to be a little bit careful here because we want 1 over cosine x, and this plus 1 is off to the side of all of that. So it's not cosine of x plus 1 and then taking the reciprocal of that. That's not what we want. We want just 1 over cosine x. Figure out that first, and then we're going to add 1 to the side. They would give us different graphs if we did it this way instead of this way. So first you have to figure out what 1 over this graph is, and then we're going to add 1 to that. So if this is cosine, 1 over it means anywhere I have zeros, those become my asymptotes. And remember, for secant, I'm expecting to see those U's going up and down, up and down. 1 over 1 stays 1. 1 over minus 1 stays negative 1. 1 over 1 stays 1. 1 over minus 1 stays minus 1, and so on. These are all positive y's, so this is going to be a positive U, a U going up. These are all negative y's, so this is going to be a negative U. Positive, oops. So U pointing up, U pointing down, and so on. Alright, now this graph in red is the graph of secant of x, 1 over cosine. I still haven't done this plus 1 that's off to the side. So now what we need to do is just take this red graph and shift everything up 1 unit. So this U right here that has this min at 1, when I shift that up, now it's up here at 2, so this is going to look like that. My asymptotes don't change, because I'm not shifting left or right, I'm just shifting up or down, so it's not going to affect my asymptotes at all. This is at a height of negative 1, When I shift that up 1, now it's going to go through 0. So it would look like this. This shifts up 1, so now my u is up a little bit higher. This shifts up 1, so my u is up higher, and so on. So the graph in blue is secant of x plus 1. Okay, let's take a look at the graph of negative tangent pi x. So we've got a negative on the outside, so that's going to cause us to have a reflection over the x-axis. So that's going to flip my tangent graphs upside down. And then we have this pi next to that x, which is going to cause us to have a horizontal compression again by a factor of 1 over pi. So that affects our period. So let's figure out what our new period is going to be. Remember, this is a tangent, so normally the period of tangent is pi, and this time we're dividing by this b, which is also pi, so the new period, those cancel out to just a 1. So here's what you're going to want to do, and I didn't provide a grid for this because those pi's cancel out, so we don't see a scale down here involving any pi's at all. It's going to just involve integers or fractions. Remember that for tangent, normally tangent looks like this with these asymptotes at minus pi over 2 to pi over 2 for a total width across here of pi. Well, now I want that total width going across to be 1. So if I want this distance between these two asymptotes to be 1 across to fit my period, then that would mean this would have to be at a half, and this would have to be at negative a half. So that's how you figure out what your scale should be. And that means the next one over would be 1 away, so this would be 3 halves, and so on. Okay, so this would be negative 3 halves. So each of these asymptotes is 1 apart from the next one. And then we're just going to draw our normal tangent graph, but reflected over the x-axis. So instead of rising up, now it's going to have to fall. So it's going to just look like that. So it's easier on these, especially when you get pi's canceling out with that period, to kind of create your own scale mark based on what you know the period is supposed to be, and just adjust your scale to fit what you want it to look like. Okay, the last one here, secant of pi over 2x minus 1. Okay, so we see this pi over 2 here, so we know that there's going to be a horizontal compression going on. And what I want to think about for this one is I'm going to think in terms of reciprocals again, and you don't have to do it this way. If you want to just work directly with your secant graph that you have memorized, you certainly can. But I'm going to think about this as 1 over cosine of pi over 2x. And then I'm going to do that shift minus 1 at the end. So we'll forget about the minus 1 temporarily. So let's think about the graph of cosine pi over 2x first. And because that has a b in there, that's that horizontal stretch or compression, and that's going to affect our period. Now when I'm doing this, I'm using cosine, so the normal period of cosine is 2 pi, and we're going to divide by this b, which is this pi over 2. So when you simplify that, you're going to leave the 2 pi where it is, and you're going to multiply by the reciprocal 2 over pi, and the pi's cancel out, and you get 2 times 2 is just 4. So this is actually a horizontal stretch because our period, or a compression, excuse me, because our period is now a little bit smaller than 2 pi would be. So here's how we're going to show that. Make your own grid. The only thing that's happening to this cosine graph is a new period. We're not shifting it up or down at all. We're not doing any kind of a phase shift. We're not changing amplitudes or anything at all. So just draw the normal U shape of a cosine graph and adjust your scale down here to be what you want the period to be. I want the period to be a width of 4. So this would start at 0, and that means this has to stop at 4. If you wanted to draw a couple more cycles, then this would have to stop at 8, and this one over here would have to stop at -4. So adjust your scale to be what you want. I didn't have an amplitude change, so this is at 1, and this is at -1. So this graph in red is cosine pi over 2x. Now we need to do the reciprocal of it to get the secant graph. So all of the zeros on this red graph become my asymptotes. So I'm going to have an asymptote here, 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 and so on. If you wanted to put some scale marks on some of those, you certainly could. Since this min is supposed to be halfway between 0 and 4, then that would be at 2, this is at 1, and this is supposed to be at 3. So these are just happening at every integer. -1, -2, -3, -4. So you could put in a few more details there in that scale if you want. Now that I know where all of my asymptotes are, we just need to draw our U-shapes. For all of these 1s and -1s, they're going to stay put because the reciprocal of 1 stays 1, reciprocal of -1 stays 1, and so forth. And then these are all positive y's, so this needs to be a U going up. These are all negative y's, so these will go down. This will go up, down, up, down, and so forth. So now this graph in blue is my secant pi over 2x. Last but not least, we want to put in that shift down 1. So each of these u's are going to get shifted down 1. Notice that's a vertical shift, so it's not going to affect these asymptotes at all. So they will stay at -1, -3, +1, +3, +5, +7, and so on. But the U moves down. So this goes down, is right now at 1. When I shift that down, it's going to go all the way down to 0. So it's just going to be this U shape at 0. This is at -1. So if I move that down, now it's going to be down here at -2. This one goes down to 0. This one goes to -2. And so on. Okay, so the graph in black is secant pi over 2x -1. Alright, again, these take some practice. Good luck graphing tangent, cotangent, secant, and cosecant functions.